Astronomers just discovered something that should not be happening. At this very moment, 7 comets are racing toward the Sun, all arriving within days of each other in October of 2025. Nothing like this has ever been recorded in human history. But here is what makes this discovery truly unsettling. 3. I-Atlas, an object from another star system entirely, is also making its closest approach during this exact same window. The odds of this are astronomically small, unless something is coordinating these arrivals. In a typical year, we might see 1, maybe 2 bright comets worth talking about. Most years pass with nothing more spectacular than a few telescopic smudges that excite only the most dedicated comet hunters. But 2025, it is like the universe decided to throw us a parade. 7 distinct comets, each carrying ice and rock from the outer reaches of our solar system, all arriving within months of each other, like some cosmic reunion nobody planned. Think of it this way. Imagine if 7 different friends from across the country all showed up at your door on the same weekend, each claiming they had no idea the others were coming. Possible, sure. Coincidental, absolutely. Suspicious enough to make you wonder if someone sent out invitations behind your back, you bet. This clustering creates what astronomers call a swarm effect. Multiple comets crowding into a relatively short observation window. From our perspective here on Earth, it looks almost orchestrated, almost like something herded them here. The pattern jumps out immediately when you look at the data. Most years, amateur astronomers spend months hunting for anything worth photographing. This year, they are spoiled for choice. Photography forums buzz with images of multiple comet tails streaking across the same patch of sky. Social media explodes with time-lapse videos showing what looks like a coordinated celestial ballet. But here is where our story takes an intriguing turn. While these 7 comets dance their predictable orbits, something else prowls the darkness between planets. 3. I-Atlas, the 3rd confirmed interstellar object ever detected in our solar system. Unlike our 7 comet welcoming committee, this visitor was not born here. It formed around another star in another planetary system, and it is passing through our neighborhood on a one-time hyperbolic trajectory. The timing raises questions that keep astronomers awake at night. Is it pure coincidence that our solar system's most unusual comet, year in recent memory, coincides with a visit from an interstellar stranger? Or could there be something more deliberate at work? Consider the implications. 7 comets do not just happen to converge without reason. In a solar system governed by the predictable laws of physics, every orbit tells a story. Every trajectory carries the fingerprints of the forces that shaped it. If something guided these objects into their current paths, those fingerprints should be detectable. The interstellar visitor adds another layer of mystery. 3 I-Atlas carries ice and dust forged in the fires of a distant star, seasoned by cosmic radiation during a journey that likely spanned millions of years. Its chemical composition holds clues about planetary formation in other solar systems. Its behavior as it approaches our Sun reveals how materials from elsewhere respond to stellar heat. But what if its arrival is not as random as we assumed? What if the same force that potentially herded 7 Earthborn comets also guided an interstellar visitor toward our solar system at precisely the right moment? The questions multiply like fractals, each answer spawning new puzzles. How would we even detect such influence? What kind of mechanism could operate across the vast distances of space to coordinate objects with such precision? And if such coordination is possible, what does that tell us about the true nature of our cosmic neighborhood? Every discovery begins with an observation that does not quite fit the expected pattern. Every breakthrough starts with someone asking why things are not quite as simple as they appear. The swarm has arrived, and with it, questions that may challenge everything we think we know about how our solar system works. Let's meet our 7 visitors individually, because each carries its own story of discovery and cosmic journey. Think of this as a lineup where every suspect has an alibi, but somehow they all ended up at the same crime scene. Pan-STARRS takes center stage as our first and brightest performer. Discovered by the Panoramic Survey Telescope and Rapid Response System, a Hawaiian-based sky patrol that has revolutionized comet hunting, this object promises to reach naked eye visibility for Northern Hemisphere observers. The timing window stretches from late March through May of 2025, giving us months to study its approach. What makes Pan-STARRS particularly intriguing is not just its brightness potential, but its orbital geometry. The comet's path brings it relatively close to our orbital plane, making it easily visible from populated latitudes. For pattern-seeking minds, this accessibility feels almost convenient. Too convenient, perhaps, for something that supposedly wandered in from the outer reaches of the Oort cloud entirely by chance. SWAN presents a different discovery story altogether. The Solar Wind Anisotropies spacecraft, designed to study solar particle streams, accidentally became a comet hunter when its hydrogen detection instruments began spotting the characteristic glow of comet atmospheres. SWAN comets often appear suddenly in the data, their hydrogen emissions announcing their presence before optical telescopes catch up. This hydrogen signature tells us something important about SWAN's activity level. Unlike dormant rocks that only brighten when solar heat awakens them, SWAN was already outgassing when discovered. It has been active for months, possibly years, creating that telltale hydrogen envelope that betrayed its location. Stereo offers perhaps the most dramatic discovery narrative. Solar observation spacecraft, positioned to monitor our star's activity, caught this comet diving toward the sun in their peripheral vision. Stereo comets often become suicidal solar grazers, racing so close to our star that they either disintegrate in spectacular fashion or emerge fundamentally altered by the experience. The timing here deserves attention. Stereo's arrival window coincides with a period of heightened solar activity when our star's magnetic field is particularly turbulent. Atlas K1 carries the weight of astronomical hype and disappointment. When the asteroid terrestrial impact last alert system first detected this object, early brightness predictions suggested it might become one of the most spectacular comets in decades. Reality, as usual, proved more modest. Atlas K1 will likely require binoculars or a small telescope for comfortable viewing. But here is what makes Atlas K1 suspicious in our investigation. Its discovery date places it squarely within the swarm timeline, yet its orbital characteristics suggest it has been following this path for thousands of years. Why are we finding it now? Why this year, when 6 other comets crowd the same observation window? Atlas G3 shares the same survey heritage as its K1 sibling, discovered by the same Hawaiian telescope system that has become remarkably efficient at finding potentially hazardous objects. What troubles careful observers is how many recent comet discoveries trace back to Atlas operations. When the same survey system discovers multiple members of an unusual swarm, patterns start to emerge that demand explanation. Comet Lemon brings a different pedigree to our cosmic gathering. The Catalina Sky Survey Station on Mount Lemmon in Arizona has been hunting near-Earth objects since the 1990s. Lemon arrives in the middle of the pack, neither leading nor trailing the group. It is positioned like a placeholder, maintaining formation with mathematical precision that seems unlikely to emerge from purely random orbital mechanics. NEAT rounds out our septet with a touch of historical irony. The Near-Earth Asteroid Tracking Program ended operations in 2007, but comets discovered during its active years continue arriving on schedule. NEAT was always going to arrive in 2025. The question is why it is arriving alongside 6 companions. The Asteroid Terrestrial Impact. Last Alert System, known simply as ATLAS, operates from 2 observatories in Hawaii. Every clear night, these robotic telescopes scan the entire visible sky, hunting for anything that moves against the background stars. The system was built to find asteroids that might threaten Earth, giving humanity enough warning to mount a defense. But ATLAS has become remarkably good at finding comets too, and in 2025, it found 2 that would become central characters in our celestial mystery. Atlas K1 appeared first in the survey data during early 2024. The discovery team ran their standard brightness calculations based on the comet's distance and the amount of sunlight it reflected. Those early numbers suggested something spectacular, a comet that might rival some of the brightest in recorded history. Social media lit up with predictions of a once-in-a-lifetime show. Astronomy websites published articles with titles about the Great Comet of 2025. Amateur astronomers began planning observation campaigns and marking their calendars. Then, reality set in. As more observations accumulated and the comet's true behavior became clear, those early predictions crumbled. Atlas K1 was not going to be a naked eye spectacle. It would require binoculars at minimum, possibly a small telescope, to see comfortably. The disappointment rippled through the astronomy community. People who had been excited about showing their children a bright comet had to adjust their expectations downward. But for our investigation, the disappointment matters less than the timing. Atlas K1 has been traveling toward the inner solar system for thousands of years. Its orbit was set in motion long before human civilization existed, shaped by gravitational encounters with the giant planets that slowly bent its path sunward. There is nothing suspicious about the orbit itself. What raises questions is the discovery timing. Why did Atlas find this particular comet during 2024, just in time for it to arrive as part of our 2025 swarm? The survey has been operating for years, scanning the same patches of sky repeatedly. If Atlas K1 was always going to arrive in 2025, it should have been detectable years earlier, when it was still in the outer solar system. Atlas G3 emerged from the same Hawaiian survey system roughly 6 months after K1. Same telescopes, same detection algorithms, same team of astronomers checking the nightly haul of moving objects. But G3 tells a different story than its sibling. While K1 disappointed with modest brightness, G3 never promised anything spectacular to begin with. It was always going to be a faint object, interesting to dedicated comet hunters, but not the kind of target that casual observers would seek out. What makes G3 significant is not its brightness, but its position in the sequence. Here we have two comets discovered by the same survey system, both arriving in 2025, both added to a swarm that already includes 5 other members. The Atlas team has discovered hundreds of asteroids and dozens of comets since operations began. Most of those discoveries are scattered randomly across time, arriving in different years as their individual orbits dictate. But K1 and G3 both converge on the same narrow window. The survey technology itself deserves examination. Atlas represents cutting-edge asteroid and comet detection capability. The system can spot objects far dimmer and more distant than older surveys could detect. This improved sensitivity means Atlas finds things that previous generations of astronomers would have missed entirely. Some researchers argue this explains the apparent clustering. We are not seeing more comets arriving in 2025. We are simply finding comets that were always going to arrive, but would have gone undetected in earlier decades. But that explanation only works if similar clustering appears in other recent years as survey technology improved. Instead, 2025 stands alone. The Atlas twins, along with their 5 companions, create a pattern that feels too organized for random chance. 2 comets from the same survey arriving in the same year, joining 5 others discovered by different systems. The odds keep stacking up in ways that make pattern-seeking minds uncomfortable. Comet Lemon carries a pedigree that commands respect in the astronomy community. The Catalina Sky Survey, operating from Mount Lemmon in the mountains of southern Arizona, has been scanning the night sky since the late 1990s. Over more than 2 decades, the survey has accumulated one of the most comprehensive databases of small solar system bodies ever compiled. When Catalina discovers something, the orbital calculations come backed by decades of experience and thousands of verified observations. The discovery of Comet Lemon happened during routine survey operations, just another faint smudge moving against background stars. The team calculated its orbit, determined it would reach perihelion in 2025, and added it to the catalogue. Nothing about the discovery itself seemed unusual. Catalina finds comets regularly as part of its near-Earth object tracking mission. But as 2025 approached and other discoveries accumulated, Lemon's position in the timeline started to look less random and more like a carefully placed piece in a larger puzzle. What makes Lemon particularly interesting is its mediocrity. This is not a bright, spectacular comet that will grace magazine covers or inspire casual observers to venture outside with binoculars. Lemon will remain a modest telescopic object throughout its passage, interesting to dedicated amateur astronomers, but invisible to anyone not actively searching for it. Yet here it sits, arriving in the same narrow window as 6 other comets, maintaining what feels like formation in the middle of the pack. The orbital geometry tells us Lemon originated in the outer solar system, likely the scattered disk region beyond Neptune, where countless icy bodies orbit in the cold darkness. Something perturbed its orbit millions of years ago, perhaps a gravitational encounter with Neptune or one of the other giant planets. That perturbation sent Lemon falling toward the inner solar system on a journey that would take geological ages to complete. The mathematics of its path show nothing unusual, nothing that suggests artificial influence or exotic physics, just gravity doing what gravity does. slowly reshaping orbits over cosmic timescales. NEAT represents something different entirely. The Near-Earth Asteroid Tracking Program operated from 1995 until 2007, when funding ended and the telescopes fell silent. But the comets discovered during those active years continue arriving on schedule, following orbits calculated decades ago. NEAT's appearance in our 2025 swarm carries a touch of prophecy, an object whose arrival was predicted long before any of the other members were even discovered. The discovery happened back in 2009, when NEAT was still being processed through the final datasets collected before shutdown. Orbital calculations showed perihelion would occur in 2025, more than 15 years in the future. The orbit has been refined through thousands of follow-up observations since then. There is no uncertainty about its path, no surprises about its timing. NEAT was always going to arrive in 2025. This foreknowledge makes NEAT both the most predictable and most puzzling member of our swarm. 6 other comets discovered across different years by different surveys all converge on the same time window. But NEAT has been sitting in the catalogues for over a decade, its arrival date known and confirmed repeatedly. If something is coordinating these arrivals, it would need to have been operating for at least 15 years, subtly nudging other comets to match NEAT's predetermined schedule. The veteran status of both Lemon and NEAT adds credibility to our investigation. These are not recent discoveries that might involve measurement errors or computational mistakes. Both comets have been tracked extensively, their orbits verified by multiple observers using different telescopes and techniques. When they arrive alongside 5 more recent discoveries, the clustering cannot be dismissed as artifact of improved detection technology or observational bias. The veterans were coming regardless, and somehow 5 others joined them. Walk into any planetarium on a typical year and ask about visible comets. The astronomer will probably sigh, check their database, and tell you about one marginal object that requires a good telescope and dark skies. Maybe, if you are lucky, there is a binocular comet that dedicated enthusiasts are tracking. Most years pass without a single naked eye comet gracing our skies. This is the baseline reality of comet watching: patience, disappointment, and occasional rewards that require serious equipment to appreciate. The general public remains blissfully unaware of the dim, fuzzy patches that excite amateur astronomers. Comets, for most people, exist only in history books and disaster movies. Children learn about Halley's Comet in school, but never expect to see anything comparable in their lifetimes. Professional astronomers spend entire careers studying comets without ever witnessing a truly spectacular apparition. This is normal. This is what comet astronomy looks like in most years across most of human history. 2025 shatters this pattern with the subtlety of a cosmic sledgehammer. 7 notable comets within months of each other. Multiple objects bright enough to photograph with ordinary cameras. Several reaching binocular visibility with at least one promising naked eye spectacle for casual observers. To understand how unusual this clustering really is, we need to examine the mathematics of comet discovery and visibility. Modern sky surveys have revolutionized our ability to detect distant objects. The Panoramic Survey Telescope and Rapid Response System, operating from Haleakala Observatory in Hawaii, scans the entire available sky every few nights. The Catalina Sky Survey in Arizona covers different patches of sky with systematic precision. NEOWISE, the space-based infrared telescope, detects the heat signatures of objects invisible to ground-based instruments. These survey programs discover hundreds of new comets and asteroids every year, but the vast majority remain forever telescopic. Only a tiny fraction ever brighten sufficiently to attract public attention. The statistical expectation for any given year is 0 to 1 object reaching naked eye brightness, with 2 or 3 additional comets becoming accessible to serious amateur observers. Yet, improved detection capabilities do not explain 2025's unusual abundance. Survey telescopes find more objects overall, but the percentage that develop into notable comets remains consistent with historical patterns. Better instruments reveal more distant, fainter objects. They do not magically create bright comets where none existed before. The key insight is that visibility depends on intrinsic properties that surveys cannot change. A comet's brightness results from its size, composition, and distance from the Sun during closest approach. These characteristics were determined millions of years ago when gravitational perturbations first nudged these objects toward the inner solar system. Modern surveys simply announce arrivals that were already inevitable. We are not seeing more bright comets because we are looking harder. We are finding bright comets that were always going to arrive in 2025, regardless of our detection capabilities. This distinction matters enormously for our investigation. If survey improvements explained the clustering, we would expect similar patterns in other recent years as telescope technology advanced. Instead, we see 2025 standing alone as an anomalous concentration of activity. Historical records provide context for evaluating the current situation. Astronomers have been systematically tracking comets for over 2 centuries, maintaining detailed catalogues of discoveries and apparitions. When we plot comet arrivals across time, most years show 0 to 2 notable objects. Occasionally, a year produces 3 comets worth public attention. 4 in a single year happens perhaps once per generation. 7 represents a statistical outlier that demands explanation beyond simple chance. The clustering becomes even more remarkable when we consider that these are not all recent discoveries. NEAT has been tracked since 2009. Lemon was discovered years ago by Catalina. These objects were coming to 2025 whether we liked it or not. And somehow, 5 additional comets joined them in the same narrow window. The telescope revolution began quietly in the early 2000s when automated survey systems started replacing human comet hunters who had dominated the field for centuries. Before automation, discovering a comet required patience, dark skies, and countless hours scanning the heavens with binoculars or small telescopes. Amateur astronomers like David Levy spent thousands of hours searching before finding their first comet. The romantic era of lone observers competing to attach their names to celestial discoveries was ending, replaced by robotic systems that never sleep and never blink. Pan-STARRS came online in 2010, scanning the entire visible sky multiple times each month with sensitivity that far exceeded what human observers could achieve. The Catalina Sky Survey expanded its operations with better cameras and faster computers. Atlas began operations in 2015, specifically designed to find asteroids that might threaten Earth, but proving equally adept at comet detection. Each new system added to our collective ability to spot faint objects that previous generations would have missed entirely. The numbers tell the story clearly. In 1990, astronomers discovered perhaps 10 to 15 new comets. By 2010, that number had jumped to 50 or 60 per year. By 2020, we were finding over 100 new comets annually. The detection revolution dramatically increased the raw count of discoveries, pulling back the curtain on a population of comets that had always been there, but remained invisible to our limited observational capabilities. But here is the critical point that separates increased detection from the 2025 anomaly. While we find more comets overall, the percentage that become bright enough for public attention remains relatively constant. Most discoveries remain forever dim, objects that only professional astronomers and dedicated amateurs ever observe. The improved surveys drag these faint comets into visibility without changing the fundamental physics that determines which objects develop into spectacular apparitions. A comet becomes bright through a combination of factors that were determined millions of years ago. Size matters. Larger objects carry more volatile materials to vaporize under solar heating. Composition matters. Some comets contain more easily sublimated ices, while others are dominated by less reactive materials. Orbital geometry matters. Comets that pass closer to the Sun experience more intense heating that drives more vigorous outgassing. All these characteristics existed before any telescope detected the object. Survey improvements allow us to announce arrivals sooner, tracking comets while they are still in the outer solar system years before perihelion. But the surveys do not create brightness where none would naturally occur. We are not making comets brighter by finding them earlier. We are simply extending our advance warning about arrivals that were predetermined by orbital mechanics operating across geological timescales. This distinction becomes crucial when evaluating the 2025 clustering. If better detection technology explained the unusual number of bright comets, we would see similar patterns in other recent years as survey capabilities improved. The years 2015 through 2020 should show progressively increasing numbers of notable comets as Atlas and other systems came online and reached full operational capacity. Instead, those years followed historical norms with one or two objects worth public attention annually. 2025 stands alone, not because our telescopes suddenly got better, but because 7 genuinely bright comets happen to be arriving in the same narrow window. These objects were always going to brighten, always going to develop impressive tails, always going to attract attention from observers worldwide. The surveys simply gave us advance notice of a convergence that was already written in the orbital mechanics of the outer solar system. Our Sun operates on an 11-year cycle that alternates between periods of relative calm and phases of dramatic activity. During solar minimum, the Sun's surface appears smooth and quiet, marked by few sunspots and minimal magnetic disturbance. During solar maximum, the surface erupts with dark sunspot clusters, massive solar flares, and violent coronal mass ejections that hurl billions of tons of magnetized plasma into space. 2025 marks a solar maximum year when our star reaches peak turbulence in its current cycle. The timing feels almost too convenient. Our most unusual comet year in recent memory coincides perfectly with the Sun's most active phase. Solar maximum occurs roughly every 11 years, so statistically, some comet apparitions will naturally overlap with active solar periods. But the convergence of 7 comets plus an interstellar visitor during a solar maximum creates a perfect storm of celestial activity that amplifies every aspect of the show we are witnessing. Solar maximum affects comet visibility in profound ways. The enhanced solar wind, that constant stream of charged particles flowing outward from the Sun, reaches higher densities and velocities during active periods. When this intensified particle stream encounters a comet's gas cloud, the interaction becomes more violent and more visually spectacular. Ion tails, those straight blue spikes that point directly away from the Sun, grow longer and brighter under solar maximum conditions. The magnetic fields carried by coronal mass ejections can twist and distort these tails, creating kinks and spirals that make modest comets appear far more active than they would during quieter solar periods. But here is what matters for our investigation. Solar activity does not create comets. It only affects their appearance after they arrive in the inner solar system. The objects themselves were already bound for 2025 encounters, regardless of what mood the Sun happened to be in. Solar maximum might make them more spectacular to observe, but it does not explain why 7 different comets chose this particular year for their solar system debuts. The correlation between solar cycles and comet activity has intrigued researchers for decades. Some studies suggest a weak statistical relationship, with slightly more bright comets appearing during solar maximum years. The proposed mechanism involves the Sun's magnetic field, which extends throughout the solar system and varies in strength with the 11-year cycle. During solar maximum, the enhanced field might interact with the outer solar system in ways that increase the rate at which comets begin their inward journeys. Gravitational perturbations from the giant planets could be amplified by magnetic effects, nudging more objects onto Sun-approaching trajectories during active solar periods. But this hypothesis remains controversial and poorly supported by observational evidence. The statistical signal is weak at best, barely distinguishable from random noise in the historical comet catalogue. Even if the correlation exists, it would predict a modest increase in comet arrivals during solar maximum, perhaps 1 or 2 extra objects per cycle. It certainly does not predict the dramatic clustering we see in 2025, where 7 comets arrive in a concentration that exceeds anything in the modern observational record. The solar maximum timing does guarantee that whatever comets arrive will put on their best possible show. Every tail disconnection event, every outburst of fresh gas from the nucleus, every interaction with the turbulent solar wind will be amplified by the enhanced space weather conditions. Photography from this year will capture phenomena that simply cannot occur during quieter solar periods. Time-lapse videos will show comet tails responding to solar storms in real time, twisting and brightening as magnetic disturbances sweep past them at millions of kilometers per hour. This visual amplification creates psychological effects that complicate objective analysis. When comets appear more active and more dramatic than usual, observers naturally search for explanations beyond normal solar heating. The spectacular appearance suggests something extraordinary must be happening, some force beyond conventional physics driving the enhanced activity. But the extraordinary element is the Sun's behavior, not the comets themselves. Remove the solar maximum conditions, and these same 7 objects would appear dimmer, less active, and less coordinated in their movements. 3 I-Atlas appeared in astronomical databases during late 2023, flagged by automated detection algorithms as an object moving on an unusual trajectory. The initial observations showed something immediately remarkable. This was not following an elliptical orbit like every native object in our solar system. The trajectory was hyperbolic, the mathematical signature of an object with enough velocity to escape the sun's gravitational embrace forever. Only 2 other objects in history had shown similar characteristics: Oumuamua in 2017 and Borisov in 2019. Both were confirmed interstellar visitors, and now we had a third. The significance of this discovery cannot be overstated. Every comet and asteroid born in our solar system remains gravitationally bound to the Sun, following elliptical paths that bring them back repeatedly over millions of years. But 3I Atlas formed somewhere else entirely, around a different star in a different stellar system. The ice and dust that make up this object condensed in an alien environment, shaped by temperatures and pressures and chemical conditions that might differ substantially from what we experience in our own solar system's formation regions. The journey to reach us likely consumed millions of years. Interstellar space is nearly empty, a vacuum so profound that atoms are separated by distances that dwarf anything we experience on Earth. 3I Atlas drifted through this void at velocities measuring tens of kilometers per second, fast enough to cross the distance between stars given enough time. Cosmic radiation bombarded the object continuously throughout its journey, altering surface chemistry and perhaps penetrating deep into the interior. By the time it entered our solar system, 3I Atlas carried the chemical fingerprints of both its birth environment and its long voyage through the darkness between stars. What makes this visitor particularly intriguing is its premature activity. Far from the Sun, where temperatures should keep any ice frozen solid, 3I Atlas has already developed a detectable coma and tail. Solar heating at these distances should be insufficient to drive the kind of outgassing that creates visible comet features. Yet observations clearly show the characteristic fuzzy appearance that distinguishes active comets from inert asteroids. This unexpected behavior suggests either an unusual composition, perhaps containing super volatile materials that vaporize at extremely low temperatures, or some internal heat source driving outgassing independently of solar warming. The timing of 3I Atlas arrival during our most unusual comet year transforms a fascinating astronomical discovery into a genuine mystery. Interstellar visitors should arrive randomly, their passages through our solar system uncorrelated with internal solar system events. The intervals between visits depend on the local density of interstellar objects drifting through our galactic neighborhood and the random geometry of their trajectories relative to our Sun's path through space. Current estimates suggest we might detect 1 interstellar visitor per decade, given our improving survey capabilities. But here, we have an interstellar stranger arriving precisely during 2025, the same year when 7 traditional solar system comets converge in unprecedented concentration. The probability calculation is straightforward but troubling. If interstellar arrivals and unusual comet clustering are independent events, their simultaneous occurrence should be correspondingly rare. The more unusual each individual phenomenon, the more suspicious their coincidence becomes. 3I Atlas will make its closest approach to the Sun during the same general timeframe when our 7 traditional comets reach peak activity. For a few months in 2025, the inner solar system will host an interstellar visitor alongside the densest concentration of active comets in modern observational history. The cosmic stage is set for either the most remarkable coincidence or the revelation of connections we do not yet understand. When astronomers encounter inexplicable patterns, they reach for two fundamental explanations: gravity and electromagnetism. These forces govern virtually everything that moves through space, from planetary orbits to the behavior of charged particles in comet tails. If something is herding 7 comets toward synchronized arrivals, it must be operating through one of these mechanisms. Gravity is the undisputed master of solar system choreography. Every object with mass warps space-time around it, creating the invisible architecture that guides planetary orbits and comet trajectories. Gravity operates across unlimited distances with mathematical precision that allows astronomers to predict celestial events centuries in advance. But gravity is remarkably weak. It requires enormous masses to produce effects noticeable across interplanetary distances. The Sun, with its overwhelming gravitational dominance, shapes the broad patterns of solar system motion. Jupiter, despite being only 1,000th the Sun's mass, still manages to influence asteroid and comet orbits through its gravitational reach. For any object to gravitationally shepherd 7 comets into coordinated arrivals, it would need mass comparable to a major planet. We are not talking about subtle nudges that accumulate over millions of years. We are discussing the kind of gravitational influence that would be immediately obvious to orbital calculators studying these objects. The mathematics are unforgiving. A comet's orbital elements, its inclination, eccentricity, and timing reflect the gravitational influences it has experienced throughout its journey. These signatures cannot be hidden or disguised. If some massive object has been steering our 7 visitors, its fingerprints would be clearly visible in their orbital characteristics. Jupiter already demonstrates how real gravitational shepherding works. The giant planet has carved gaps in the asteroid belt, captured families of Trojan asteroids that follow its orbit, and redirected countless comets through gravitational encounters. We can measure these effects precisely, calculate the responsible forces, and predict future interactions with confidence. This gives us a template for detecting hidden shepherding. If some unknown massive object has influenced our 7 comet swarm, we should see consistent orbital perturbations, shared gravitational signatures, or synchronized changes that point toward a common cause. The absence of such signatures would effectively rule out gravitational coordination. Electromagnetic effects offer a different but equally constrained possibility. Comets carry electric charges as solar radiation ionizes their gas clouds, and moving charges respond to magnetic fields in measurable ways. The solar wind, that constant stream of charged particles flowing outward from our star, shapes comet ion tails and can produce dramatic disconnection events during magnetic storms. But electromagnetic forces work quite differently from gravity. They affect comet tails and atmospheric behavior without significantly altering orbital trajectories. A comet's tail might twist and fluctuate in response to solar magnetic activity, but the comet itself continues following its gravitationally determined path with stubborn precision. The idea that electromagnetic fields could steer 7 comets into coordinated arrivals faces insurmountable physics problems. Such steering would require magnetic field strengths far exceeding anything observed in the solar system, and the energy requirements would dwarf the output of the Sun's emissions. Moreover, electromagnetic effects produce characteristic signatures in comet spectra and tail behavior that would be impossible to hide. If powerful magnetic fields were manipulating our 7 visitors, every observatory studying these objects would detect the telltale signs immediately. Let's apply detection criteria systematically to our 7 comet cast. Do Pan-STARRS, SWAN, Stereo, Atlas K1, Atlas G3, Lemon, and NEAT share orbital characteristics that suggest common influences? The electromagnetic environment of the solar system offers a second potential mechanism for coordinating comet arrivals. Unlike gravity's invisible grip that shapes orbits over millions of years, electromagnetic forces operate through the interaction of charged particles and magnetic fields. When solar radiation strips electrons from comet gases, the resulting ions become responsive to magnetic fields in ways that neutral atoms never experience. The solar wind carries these magnetic fields outward from the Sun, creating a dynamic environment where charged particles can be pushed, pulled, and redirected by forces that have nothing to do with mass or gravity. Comet ion tails provide the most visible evidence of electromagnetic effects in action. These straight blue spikes always point directly away from the Sun, regardless of the comet's direction of motion. The orientation results from solar wind pressure, pushing ionized gases along magnetic field lines that stream outward from our star. During quiet solar conditions, ion tails develop smooth, regular structures that extend for millions of kilometers. During solar storms, when coronal mass ejections hurl particularly dense, magnetized plasma into space, the tails can twist, kink, or disconnect entirely as magnetic field lines reconnect in violent configurations. These tail phenomena demonstrate that electromagnetic forces definitely affect comets. The question is whether such forces could influence orbital trajectories rather than just atmospheric appearance. The physics here are unambiguous and unforgiving. Electromagnetic forces act on charged particles, not on bulk masses. A comet nucleus, the solid chunk of ice and rock at the center, remains electrically neutral overall despite surface charging effects. The gravitational forces that determine its orbit dwarf any electromagnetic influences by many orders of magnitude. Consider the energy requirements for electromagnetic orbit modification. Changing a comet's trajectory requires applying force over extended periods, fighting against the Sun's gravitational pull that dominates motion throughout the inner solar system. The magnetic fields present in the solar wind, while capable of creating spectacular tail effects, are far too weak to produce measurable orbital changes. You would need field strengths comparable to those near neutron stars or black holes to generate forces sufficient for trajectory modification. Such extreme fields would produce obvious signatures across the entire solar system, affecting every charged particle and magnetized object within range. The solar wind itself varies with the 11-year solar cycle, reaching peak intensity during solar maximum, when enhanced particle streams flow outward at higher velocities and densities. But even during these active periods, the forces remain confined to affecting tenuous gas clouds rather than solid comet nuclei. The 2025 solar maximum will create dramatic visual effects as stronger magnetic fields interact with comet atmospheres, but it cannot explain why 7 different comets arrived in this particular year rather than spreading their appearances across the decade surrounding solar maximum. If electromagnetic forces were somehow steering our 7 visitors, the spectroscopic signatures would be unmistakable. Unusual emission lines would appear in comet spectra, indicating gas populations experiencing forces beyond normal solar-wind interaction. Tail behaviors would show systematic deviations from predictions based purely on solar-wind models. The timing of disconnection events would correlate with something other than observed solar activity. None of these signatures appear in the data collected so far. The electromagnetic hypothesis faces an additional challenge when we consider 3I Atlas. An interstellar visitor carries no special electromagnetic properties that would allow it to coordinate the movements of solar system natives. Its magnetic field, if it has one, would be negligibly weak compared to the Sun's influence. Any electromagnetic signaling between objects would require power sources and transmission equipment that we should easily detect with current radio astronomy capabilities. Every comet carries a detailed history written in the mathematics of its orbit. The path an object follows through space reflects every gravitational encounter it has experienced, every perturbation from passing planets, every subtle influence that has shaped its trajectory over millions of years. Orbital forensics involves reading this history backward, tracing current positions and velocities back through time to understand where objects came from and what forces brought them to their present circumstances. Pan stars originates from the Oort cloud, that vast spherical shell of icy bodies surrounding our solar system, at distances measuring tens of thousands of astronomical units. Something perturbed its orbit perhaps 1 million years ago, possibly a passing star whose gravity rippled through the outer solar system, nudging countless objects onto new paths. Pan stars fell inward following the elegant mathematics of gravitational mechanics. Its arrival time in 2025, predetermined by that ancient perturbation and the Sun's unchanging gravitational field. Swan tells a different story. Its orbital inclination suggests origins in a different region of the Oort cloud, perturbed by different forces at a different time. The hydrogen activity that led to its discovery indicates a composition rich in water ice, probably formed in the cold outer regions of the primordial solar nebula before being scattered outward by gravitational interactions with the forming giant planets. Swan's current trajectory shows no evidence of recent perturbations beyond the expected influence of Jupiter and Saturn as it passes through the inner solar system. Stereo follows the most extreme path of our 7 visitors, diving so close to the Sun that it will experience temperatures capable of vaporizing rock. This sun-grazing trajectory developed through a series of gravitational encounters that gradually reduced the comet's perihelion distance over multiple orbits. Each passage through the inner solar system brought it slightly closer to the Sun as planetary perturbations modified its path. The orbital history is complex, but entirely explainable through conventional gravitational interactions operating over thousands of years. Atlas K1 and Atlas G3, despite sharing discovery circumstances, tell independent orbital stories. K1 approaches from a different angle than G3, with inclination and eccentricity values that place their formation regions in separate parts of the outer solar system. Their simultaneous arrival in 2025 results from independent perturbations that happened at different times in different locations. The twins share only their discovery survey and arrival year, not their gravitational histories. Lemon's orbital elements reveal a scattered disk origin. that population of objects beyond Neptune whose orbits were disrupted by gravitational interactions with the ice giant planets during the solar system's youth. The orbit shows signatures of a close Neptune encounter roughly 50,000 years ago that sent the comet on its current Sun approaching trajectory. The timing of that encounter, not any recent influence, determines why Lemon arrives in 2025 rather than some other year. NEAT carries the longest documented orbital history of any member in our swarm. 15 years of observations have refined its orbital elements to extraordinary precision. We know exactly where NEAT came from, exactly which gravitational influences shaped its path, and exactly when it will reach perihelion. The orbit is so well determined that predictions made a decade ago match current observations to within measurement uncertainty. NEAT provides an anchor point, an object whose arrival was predicted long before the other swarm members were even discovered. When we compare all 7 orbits systematically, searching for common signatures that might indicate shared influences, we find nothing. Each comet approaches from a different direction. Each carries different inclination relative to the ecliptic plane. Each shows different eccentricity and different timing in its orbital period. The source regions span the entire outer solar system, from the scattered disk to the inner Oort cloud to the classical Oort cloud populations. 3I Atlas carries credentials that no solar system native can claim. This visitor formed in the protoplanetary disk surrounding a star whose light has never been seen by human eyes. The ice and dust that compose this object condensed under conditions that might differ substantially from those that shaped our own comet populations. Temperature gradients in that alien disk, the abundance of heavy elements in the parent star, the timing and violence of planetary formation processes, all these factors influenced what materials ended up in this wandering chunk, now passing through our neighborhood. Spectroscopic analysis provides our primary tool for reading 3I Atlas's chemical biography. When sunlight strikes the comet's surface and vaporizes volatile materials, each molecular species produces characteristic emission lines at specific wavelengths. Water creates signatures in both visible and infrared wavelengths. Carbon monoxide shows up as distinct features in ultraviolet spectra. Organic compounds leave fingerprints that reveal their molecular structure. By cataloging which emission lines appear and measuring their relative strengths, astronomers can determine what this interstellar visitor is made of. Early spectroscopic observations revealed something immediately interesting. 3I Atlas shows strong carbon monoxide emission at distances where water-dominated comets remain relatively inactive. Carbon monoxide sublimates at much lower temperatures than water ice, around -200 degrees Celsius, compared to water's 0-degree threshold. This suggests that 3I Atlas either formed in an extremely cold environment where carbon monoxide could condense as ice, or that it has a composition fundamentally different from typical solar system comets, where water dominates the volatile inventory. The premature activity raises questions about internal structure. Solar heating at 3I Atlas's current distance should barely affect surface ice, certainly not enough to create the visible coma and tail that observations clearly show. Either the composition includes highly volatile materials that respond to minimal solar input, or some internal heat source drives outgassing independent of external warming. Radioactive decay of elements like aluminum-26 could provide such internal heating if the comet formed quickly enough after its parent star's supernova to incorporate short-lived isotopes. Alternatively, tidal stresses from passing near another star during its interstellar journey might have deposited heat that continues driving activity. The dust-to-gas ratio in 3I Atlas's coma provides additional clues about formation conditions. Solar system comets typically eject comparable amounts of dust and gas as they approach the Sun, creating the characteristic double tail structure, where white dust curves along the orbit, while blue ion gases stream straight away from the Sun. If 3I Atlas shows a different ratio, it might indicate that dust and ice mix differently in its formation environment. Perhaps the parent star's protoplanetary disk contained more or less dust than our own solar nebula. Perhaps different condensation temperatures led to ice and dust separating into distinct layers rather than forming a homogeneous mixture. The rotation period, revealed through brightness variations as different parts of the nucleus reflect sunlight toward Earth, tells us about the object's physical structure and formation history. Most comets rotate with periods measured in hours, the result of collisions and gravitational interactions during their formation. If 3I Atlas shows an unusual rotation period or unexpected brightness variations, it might indicate a shape or internal structure that developed under different conditions than solar system comets experienced. Size estimates based on brightness measurements and assumed reflectivity suggest 3I Atlas measures perhaps 1 to 2 kilometers across, comparable to many short-period comets in our system, but smaller than the largest Oort cloud visitors. The path 3I Atlas follows through our solar system tells a story of cosmic wandering that began in another stellar neighborhood entirely. Unlike the elliptical orbits that trap planets and native comets in endless cycles around the Sun, this visitor travels on a hyperbolic trajectory. The mathematics are unambiguous. 3I Atlas arrived with enough velocity to escape solar gravity permanently. After swinging past the Sun, it will accelerate back toward interstellar space, never to return. The hyperbolic excess velocity, the speed the object maintains, even after escaping the Sun's gravitational influence, measures approximately 3 kilometers per second. This number tells us that 3I Atlas was not captured from interstellar space by some chance gravitational encounter. It was already moving through the galaxy when it happened to pass close enough to our solar system for the Sun's gravity to bend its path. The trajectory calculations work backward to suggest possible origin points, though pinpointing the exact source star remains impossible with current data. The approach direction places 3I Atlas coming roughly from the constellation Perseus as seen from Earth. But constellations are merely human patterns imposed on stars at vastly different distances. The actual origin could be any star within a sphere hundreds of light years across, moving in any direction through the galaxy's rotation. The interstellar visitor might have been traveling for 1 million years or 10 million years, drifting through the near vacuum between stars at velocities that seem fast by human standards, but are glacially slow compared to the vast distances involved. What makes this trajectory particularly relevant to our investigation is its inclination relative to the ecliptic plane. 3I Atlas does not plunge through our solar system from high galactic latitudes. Instead, it approaches at a modest angle, keeping it within the general vicinity of the planetary disk for an extended period. This geometry means the interstellar visitor spends months moving through the same region of space, where our 7 traditional comets execute their solar approaches. The distances remain vast by terrestrial standards. 3. I-Atlas never comes closer than several astronomical units to any of the 7 swarm members. Direct gravitational encounters are impossible at such separations, but the shared occupancy of similar orbital space creates at least the geometric possibility for subtle influences that might not be detectable through conventional observations. If some form of interaction exists between the interstellar visitor and solar system natives, the trajectory provides the spatial context where such interaction could theoretically occur. The retrograde motion adds complexity to the geometric analysis. While most solar system objects orbit the Sun in the same direction the planets rotate, 3I Atlas approaches from the opposite direction. This retrograde motion creates relative velocities between the interstellar visitor and traditional comets that exceed what any solar system natives experience during normal gravitational encounters. High relative velocities typically minimize gravitational interaction effects because fast-moving objects spend less time within each other's gravitational influence zones. The orbital nodes, points, where 3I Atlas crosses the ecliptic plane, occur at precisely calculable dates. The ascending node, where the trajectory passes from below to above the plane, happens in early 2025. The descending node, crossing back downward, occurs several months later. These crossings represent moments when the interstellar visitor comes closest to the general region occupied by traditional comets and their debris trails. The solar wind flows outward from our Sun at all times, a constant stream of charged particles that fills the space between planets with an invisible plasma. During solar minimum, this wind maintains relatively steady velocities around 400 kilometers per second, carrying magnetic field lines outward in smooth, predictable patterns. During solar maximum, the wind becomes turbulent and violent. Coronal mass ejections hurl billion-ton bubbles of magnetized plasma into space at speeds exceeding 2,000 kilometers per second. High-speed streams from coronal holes create shock waves that ripple through the interplanetary medium. The entire space environment becomes dramatically more active and unpredictable. 2025 marks a solar maximum year, when these violent conditions reach their peak intensity. Every comet passing through the inner solar system will experience this enhanced space weather environment. The effects on comet tails are immediate and spectacular. Ion tails, formed when solar ultraviolet radiation strips electrons from comet gases, respond directly to magnetic fields carried by the solar wind. During quiet conditions, these tails develop smooth structures that point steadily away from the Sun. During solar storms, the tails twist, kink, and sometimes disconnect entirely as magnetic field lines undergo violent reconnection events. Tail disconnection creates some of the most dramatic comet photography possible. The process begins when a coronal mass ejection carries a magnetic field with opposite polarity to the field already threading through the comet's ion tail. When these opposing fields meet, they cannot coexist peacefully. The magnetic topology reorganizes suddenly and violently, severing the connection between the comet's nucleus and its existing tail. The old tail drifts away as an orphaned cloud of ionized gas, while a new tail begins forming in the restructured magnetic environment. 2. Observers watching in real time. The comet appears to shed its tail on command, as if responding to some external control signal. But the physics are entirely natural and well understood. Solar storms affect all comets simultaneously because they all share the same space weather environment. A single large coronal mass ejection can trigger tail disconnections in multiple comets if they happen to be positioned where the magnetic disturbance passes. This creates apparent synchronization that has nothing to do with communication or coordination between the objects themselves. The comets are simply responding independently to the same external stimulus, like multiple weather vanes, all pointing in the same direction during a windstorm. The enhanced solar activity of 2025 guarantees frequent opportunities for such spectacular events. Solar physicists predict dozens of major coronal mass ejections during the months when our 7-comet swarm reaches peak activity. Each eruption will propagate outward from the Sun at predictable velocities, reaching different comet locations at calculable times based on their distances and positions. By monitoring space weather conditions at Earth and tracking the propagation of solar disturbances, we can predict when individual comets should experience enhanced activity or possible tail disconnections. This predictive capability provides crucial context for evaluating claims about coordinated comet behavior. If unusual tail events occur in multiple comets simultaneously, the first check must be for documented solar storms that could explain the timing. Only after accounting for known space weather influences can we legitimately consider more exotic explanations. The solar maximum environment creates a background of natural variability that must be understood and filtered out before any subtle coordinated behaviors could be detected. Amateur observers contribute essential monitoring of space weather effects on comet tails. Professional observatories cannot provide continuous coverage of 7 different comets across multiple months, but amateur astronomers worldwide, equipped with increasingly sophisticated cameras and telescopes, fill the gaps with distributed observation networks that document tail behavior in unprecedented detail. The infrastructure that supports modern civilization operates on assumptions of stability that space weather can violate without warning. Electrical power grids spanning continents depend on transformers and transmission lines that were never designed to handle the geomagnetically induced currents that solar storms can create. When a coronal mass ejection slams into Earth's magnetosphere, the resulting magnetic field variations induce electrical currents in long conductors like power lines. These currents can overwhelm protective systems and damage expensive equipment that takes months or years to replace. The March 1989 geomagnetic storm demonstrated how quickly space weather can translate into terrestrial consequences. Quebec's entire electrical grid collapsed within 90 seconds as transformers overloaded and circuit breakers tripped in cascading failures. 6 million people lost power during a cold Canadian night. The province remained partially blacked out for 9 hours, while utility workers struggled to restore service. That storm occurred during solar maximum, just like the conditions we face in 2025. Satellite systems face even more direct exposure to solar particle bombardment. Communication satellites, GPS navigation networks, weather monitoring systems, all orbit above the protective bubble of Earth's atmosphere, where charged particles from solar storms can penetrate spacecraft shielding. High-energy protons and electrons damage sensitive electronics through ionization effects that create false signals or permanent component failures. During severe storms, satellite operators sometimes power down non-essential systems to minimize exposure, accepting temporary service disruptions to prevent permanent damage. Aviation adds another layer of concern during periods of intense solar activity. High-altitude flight routes over polar regions pass through areas where Earth's magnetic field provides minimal shielding against cosmic radiation. During major solar storms, radiation levels can spike to doses that exceed safe exposure limits for flight crews and passengers. Airlines routinely reroute flights to lower latitudes during severe space weather events, adding flight time and fuel costs to avoid the enhanced radiation zones near the poles. The 2025 solar maximum guarantees frequent opportunities for these technological vulnerabilities to manifest. Space weather forecasters predict dozens of significant geomagnetic storms during the year, with perhaps several reaching the severe category that threatens power grids and forces flight rerouting. The timing coincidence with our unusual comet activity creates dangerous opportunities for misattribution. When power outages occur or satellite systems fail during periods of high comet visibility, the temporal correlation invites speculation about exotic causal connections. But the physics are clear, and the monitoring systems are comprehensive. Solar storms affect both technological infrastructure and comet behavior through completely independent mechanisms. Comets respond to enhanced particle density and magnetic field variations in the space environment around them. Earth's technology responds to geomagnetically induced currents and radiation bombardment. Both phenomena share common timing because they both result from the same solar eruptions, not because comets somehow influence terrestrial systems. Space weather monitoring networks provide real-time tracking of solar activity, from eruption through propagation to Earth impact. The NOAA Space Weather Prediction Center issues forecasts and warnings with the same operational urgency applied to terrestrial severe weather. When infrastructure problems occur, these monitoring systems allow precise correlation with documented space weather events. If failures happen during periods of confirmed geomagnetic storms, solar causes become far more plausible than mysterious comet influences. Human brains evolved to detect patterns because missing genuine patterns could prove fatal in ancestral environments. A rustle in the grass might be wind, or might be a predator. The cost of ignoring a real threat far exceeded the cost of occasionally jumping at shadows. Natural selection favored pattern recognition systems tuned toward false positives, brains that saw connections even when none existed, because the alternative could mean death. This evolutionary heritage serves us well in many contexts, but creates problems when we apply pattern-seeking tendencies to cosmic events, operating on scales that dwarf human intuition. When multiple unusual events cluster together, we instinctively search for underlying causes, rather than accepting coincidental timing. The response feels rational and appropriate, because in our ancestral environment, clustered unusual events usually did have common causes. Simultaneous changes in animal behavior, weather patterns, and plant growth genuinely predicted seasonal transitions or approaching storms. But the universe operates on different scales than the African savanna where human cognition evolved. Celestial mechanics follows mathematics that produces clustering through purely random processes. When you flip a coin enough times, you will eventually see long sequences of heads or tails that feel impossible but are mathematically inevitable. The human mind struggles to accept these clusters as natural products of randomness because our intuitive probability sense developed for small sample sizes in immediate survival contexts, not for evaluating rare events across cosmic timescales. The 7-comet convergence of 2025 triggers exactly this kind of pattern-seeking response. 7 objects arriving within months of each other feels too organized for randomness. Our intuitive sense of probability rebels against accepting such clustering as mere coincidence. The brain automatically searches for coordination mechanisms, hidden influences, purposeful arrangement. This response happens below conscious awareness, generating the feeling that something must be orchestrating these arrivals before rational analysis even begins. The presence of 3I Atlas amplifies the pattern-seeking response exponentially. An interstellar visitor arriving during our most unusual comet year provides exactly the kind of mysterious timing that human cognition interprets as purposeful rather than coincidental. The narrative practically constructs itself. Alien probe arrives, comet swarm follows, something significant must be happening. The story satisfies multiple psychological needs simultaneously by providing explanation for unusual timing, assigning agency to apparently random events, and positioning observers as witnesses to historically meaningful developments. Social media algorithms exploit these pattern-seeking tendencies for commercial purposes. Content suggesting mysterious connections between celestial events generates engagement metrics that drive platform economics. Videos proposing coordination mechanisms receive more views than careful explanations of orbital mechanics and statistical probability. Each share and comment feeds the algorithm, which responds by promoting similar content to wider audiences. The system amplifies pattern-seeking biases by rewarding content that triggers those biases most effectively. The challenge for objective analysis lies in separating legitimate statistical anomalies from clustering that feels meaningful to pattern-seeking brains but falls within normal variation. We need measurable criteria for determining when patterns exceed reasonable coincidence bounds. Statistical analysis provides such frameworks through probability calculations that quantify how likely apparent patterns are to emerge from random processes. When observed clustering falls within expected ranges for random distribution, coincidence becomes the most parsimonious explanation, regardless of how coordinated the timing appears. Throughout human history, bright comets have served as celestial messengers that cultures interpreted according to their deepest fears and highest aspirations. The sudden appearance of a brilliant object in the night sky, moving against the fixed patterns of stars and planets, demanded explanation in eras when astronomy and astrology remained indistinguishable. Ancient civilizations developed elaborate systems for reading cosmic omens, correlating celestial events with earthly consequences in ways that shaped political decisions and military campaigns. Chinese astronomers maintained the most meticulous comet records of any ancient civilization. The imperial court employed professional skywatchers whose careers depended on detecting and reporting unusual celestial phenomena. Comets received particular attention as broom stars that swept away old orders to make way for new ones. The Han Dynasty historical records describe dozens of comet appearances, each carefully correlated with subsequent events. Dynastic changes, natural disasters, military victories and defeats all became linked to celestial timing in a vast database of cosmic correlation. The correlation patterns reveal more about human psychology than celestial influence. When comets appeared during stable periods, chroniclers recorded them without dramatic interpretation. But when comets coincided with political upheaval or natural disasters, the temporal association became permanent in historical memory. The same cognitive bias that makes modern observers see coordination in our 2025 swarm led ancient astronomers to perceive causal connections between independent events that happened to overlap in time. Medieval European chroniclers inherited this tradition of comet interpretation through classical sources and developed their own frameworks for reading celestial omens. The Great Comet of 1066 appeared in April of that year, months before the Norman invasion of England that culminated in the Battle of Hastings. The Bayeux Tapestry immortalized the comet as a harbinger of Saxon defeat, depicting terrified observers pointing at the sky, while Harold receives news of the celestial warning. Whether the comet actually influenced events or simply provided convenient symbolism remains debatable, but the correlation embedded itself permanently in historical consciousness. The 1758 return of Halley's Comet occurred during the 7 Years' War, a global conflict that reshaped political boundaries across 3 continents. Colonial American observers interpreted the comet as an omen of independence from British rule. European astronomers celebrated it as confirmation of Newtonian gravitational theory that allowed Edmund Halley to predict the return decades after his death. The same celestial event supported completely different narratives, depending on cultural context and political aspirations, demonstrating how human interpretation shapes meaning extracted from objective phenomena. The pattern continues through modern history. Bright comets in 1811 coincided with Napoleon's Russian campaign. The Great Comet of 1843 appeared during a period of revolutionary upheaval across Europe. Comet Kohoutek's disappointing 1973 apparition occurred during the oil crisis and Watergate scandal. In each case, the temporal correlation invited speculation about causal connections that careful analysis fails to support. These historical examples illustrate how human minds naturally link clustered unusual events into coherent stories that feel more meaningful than random coincidence. When multiple dramatic phenomena occur simultaneously, whether comets, wars, plagues, or social upheavals, we instinctively search for underlying connections rather than accepting independent causation. This storytelling tendency becomes particularly pronounced during periods of social stress or uncertainty, when populations actively seek signs about future directions. The infrastructure of modern media operates on principles fundamentally different from the editorial gatekeeping that dominated information distribution for most of human history. Social media platforms prioritize engagement over accuracy, using algorithms designed to maximize time spent scrolling and clicking. Content that triggers strong emotional responses, whether wonder, fear, or outrage, receives algorithmic promotion regardless of factual validity. A carefully researched explanation of orbital mechanics competes at a disadvantage against sensational speculation about alien coordination or impending doom. Video editing software now provides amateur content creators with production capabilities that would have required professional studios just decades ago. Anyone with basic technical skills can produce compelling narratives combining real comet imagery with dramatic music, suggestive narration, and carefully selected visual effects. These productions achieve production values indistinguishable from professional documentaries while promoting theories that would never survive peer review in scientific journals. The democratization of content creation means quality no longer correlates with distribution reach. The 2025 comet swarm arrives into this media environment perfectly optimized for viral amplification. Multiple bright comets provide genuine astronomical spectacle that captures initial attention through legitimate wonder. The presence of 3i Atlas adds mysterious timing that invites speculation about coordination mechanisms. The solar maximum conditions create dramatic visual effects that make modest comets appear more active than usual. Every element combines to produce content that algorithms recognize as highly engaging and aggressively promote to wider audiences. Multiple independent creators often converge on similar interpretations without coordinating their efforts. When one video proposing alien involvement gains traction, others follow with variations on the theme. Each retelling adds new details, connections, and interpretations that gradually diverge from verifiable observations toward pure speculation. The distributed nature of this storytelling process creates the appearance of widespread consensus around ideas that might lack any factual foundation. Viewers encountering multiple videos making similar claims naturally assume some underlying truth must exist to explain the consistency. The narrative evolution happens rapidly through feedback loops between creators and audiences. Videos suggesting coordination mechanisms receive more views and positive comments than careful astronomical explanations. Creators notice which content performs well and produce more of it, refining their approaches based on engagement metrics. The most successful formats get copied and adapted by other creators seeking similar success. Within weeks, a simple observation that 7 comets arrive in 2025 transforms into elaborate narratives about cosmic significance, hidden forces, or impending transformation. Platform recommendation algorithms accelerate this process by creating filter bubbles where users primarily see content confirming their existing beliefs. Someone who watches one video about mysterious comet coordination receives recommendations for similar content. The algorithm interprets engagement with speculation as preference for more speculation, gradually constructing an information environment where alternative explanations become invisible. Users can spend hours consuming content about the 2025 swarm without ever encountering straightforward astronomical explanations of orbital clustering. Professional astronomy faces increasing challenges competing for attention in this environment. Institutional voices, speaking carefully about uncertainties and limitations, sound less authoritative than confident assertions about hidden meanings. The scientific process of hypothesis testing and evidence evaluation translates poorly into short-form video content, optimized for algorithmic promotion. Educational institutions lack both the resources and incentives to produce content at the volume and velocity that commercial creators achieve through engagement-driven business models. The most provocative interpretation of our 7 comet convergence requires examining a hypothesis that pushes far beyond conventional astronomy. Could 3i Atlas be an artificial probe from another civilization? And might the traditional comets represent a coordinated response to its arrival? This scenario demands extraordinary evidence, but the implications are so profound that dismissal without investigation would be equally unscientific. An engineered object traveling between stellar systems would need to solve problems that challenge current human technology. Propulsion across interstellar distances requires velocities measuring significant fractions of light speed to complete journeys within reasonable timeframes. Nuclear pulse propulsion, where successive atomic detonations push a spacecraft forward, represents one theoretical approach. Antimatter engines, converting matter directly into thrust with perfect efficiency, offer another possibility. More exotic solutions might involve physics we have not yet discovered, space-time manipulation or quantum effects that allow shortcuts through conventional distances. The energy requirements alone stagger comprehension. Accelerating even a modest probe to 10% of light speed demands power outputs equivalent to years of total solar energy collection. Advanced civilizations might harness their entire star's output through megastructures or tap energy sources we cannot yet imagine. But the engineering challenges remain formidable regardless of available power. Every gram of spacecraft mass multiplies the energy requirements, creating powerful incentives for miniaturization and efficiency that might produce probes radically different from human expectations. Navigation presents equally daunting problems. 3. iAtlas demonstrates remarkable precision in targeting our solar system, from launch points potentially hundreds of light-years distant. Stars move through the galaxy at velocities measuring tens of kilometers per second. Accurate targeting requires detailed knowledge of stellar positions and motions across the millions of years a probe might spend in transit. The launching civilization would need observational capabilities and computational resources far exceeding our own to plot trajectories that remain accurate across such timescales. But these engineering challenges, while impressive, do not violate known physics. Advanced civilizations might reasonably develop technologies implementing principles we understand but cannot yet harness. The question is not whether such probes are theoretically possible, but whether 3iAtlas exhibits characteristics distinguishing artificial from natural objects. Spectroscopic analysis provides our most direct tool for this evaluation. Natural comets display emission lines characteristic of water ice, carbon compounds, and simple molecules forming readily in cold stellar system environments. Artificial probes might contain manufactured materials that leave distinctive spectral signatures. Refined metals show emission patterns different from naturally occurring mineral compositions. Synthetic compounds, created through industrial processes rather than natural chemistry, would produce anomalous spectral features. Any detection of clearly manufactured substances would constitute compelling evidence for engineered construction, while purely natural spectra argue strongly against artificial origin. The spectrum of 3iAtlas, when analysed with sufficient detail, should reveal whether its composition matches expectations for natural comet materials, or includes signatures suggesting artificial origin. Behavioural analysis offers another avenue for detecting artificial characteristics in 3iAtlas. Natural comets follow ballistic trajectories determined entirely by gravitational forces and occasional outgassing that create small but measurable thrust effects. These non-gravitational forces arise when sublimating ice jets from specific locations on the rotating nucleus, creating rocket-like effects that slightly modify the orbit over time. The changes are predictable based on comet activity levels and rotation periods, producing orbital perturbations that match theoretical expectations. Artificial probes might demonstrate course corrections, attitude changes, or other maneuvers indicating active control rather than passive response to environmental forces. Even subtle control inputs would accumulate over the months of observation, producing orbital deviations that careful astrometric tracking could detect. The orbital elements of 3I Atlas show no evidence of non-gravitational perturbations beyond what natural outgassing could produce. Its trajectory appears consistent with a passive object following physics rather than engineering. However, subtle control inputs might remain below current detection thresholds, particularly if designed to mimic natural comet behavior. An advanced probe attempting to avoid detection could use outgassing plumes for attitude control, pulsing jets in patterns that appear random but actually maintain desired orientation. The spacecraft could time its maneuvers to coincide with natural activity increases as solar heating intensifies, hiding intentional changes within the noise of normal comet behavior. Such sophisticated camouflage would require detailed knowledge of how natural comets behave, suggesting prior observation and study of solar system objects. Communication signatures represent perhaps the most definitive test for artificial origin. Operating probes would likely maintain contact with their creators through radio transmissions, laser pulses, or other electromagnetic signals detectable by terrestrial radio telescopes. The search for extraterrestrial intelligence community has protocols for analyzing such signals and distinguishing artificial from natural radio sources. Systematic monitoring of 3I Atlas across multiple frequency bands has detected no obvious artificial signals, though analysis continues as the object approaches closer to Earth. The absence of detectable transmissions does not eliminate artificial origin possibilities. Advanced civilizations might use communication methods we have not conceived, exploiting physics beyond current understanding. They might encode messages in neutrino beams that pass through matter undetected by our instruments. They might employ quantum entanglement for instantaneous communication across interstellar distances. Or they might simply operate on frequencies we are not monitoring, using bandwidth outside the ranges that SETI programs traditionally search. The coordination hypothesis extends artificial origin speculation to our 7 traditional comets, suggesting they represent some form of engineered fleet responding to 3I Atlas arrival. This scenario requires even more extraordinary assumptions about advanced technology and strategic planning across interstellar distances. Each member of our comet swarm would need independent propulsion and navigation capabilities sophisticated enough to coordinate arrivals within narrow time windows. The logistics boggle human imagination. 7 different objects launched from potentially different locations at different times, all arriving within months of each other after journeys spanning millennia. Yet, the orbital characteristics of our 7 traditional comets show clear signatures of solar system origin. Their compositions match expected patterns for objects formed in our outer system. Their discovery histories trace back to well-documented survey programs tracking these objects for years or decades. Their trajectories show no evidence of artificial course corrections or coordinated maneuvers. If these 7 comets represent artificial constructs masquerading as natural objects, they would need camouflage capabilities sophisticated enough to deceive every instrument pointed at them. Modern spectroscopy identifies molecular species with extraordinary precision, distinguishing between isotopic ratios that reveal formation environments and evolutionary histories. Any artificial probe attempting to mimic a natural comet would need to carry materials matching the exact composition expected for objects formed in our outer solar system billions of years ago. The isotopic signatures pose particular challenges for hypothetical camouflage operations. Different stellar environments produce different ratios of hydrogen to deuterium, oxygen-16 to oxygen-18, carbon-12 to carbon-13. These ratios serve as cosmic fingerprints, identifying where materials formed and what processes shaped them. Solar system comets carry isotopic signatures, consistent with formation in our primordial solar nebula. If any of our 7 visitors showed anomalous ratios suggesting formation elsewhere, spectroscopists would immediately flag the discrepancy. Outgassing behavior creates additional camouflage requirements. Natural comets develop their characteristic appearance through sublimation of volatile materials under solar heating, a process depending on internal structure, composition, and thermal properties developed over geological timescales. The brightness variations, jet formations, and tail development all follow predictable patterns based on how ice responds to increasing solar radiation. Artificial mimicry would require sophisticated engineering to replicate behaviors that emerge naturally from comet physics. The rotation periods revealed by brightness variations reflect natural tumbling motion of irregularly shaped objects under minimal gravitational binding. Artificial spacecraft might maintain controlled orientation for antenna pointing or solar panel alignment, producing rotation patterns too regular or too stable compared to natural tumblers. Careful photometric monitoring over weeks and months should reveal whether objects spin like natural rubble piles or like engineered platforms maintaining deliberate attitudes. Communication requirements for fleet coordination present another vulnerability in camouflage scenarios. 7 distributed objects, plus a command vessel, would need frequent data exchange to maintain synchronized operations. Radio transmissions, laser communications, or other electromagnetic signals would carry information between fleet elements on timescales relevant to human detection capabilities. The SETI community operates radio telescopes, continuously monitoring for exactly these kinds of artificial signals. Project Breakthrough. Listen, the most comprehensive search for technological signatures ever undertaken, scans millions of frequency channels across wide swaths of sky. The program would detect coordinating transmissions between our alleged fleet members if they operate on frequencies within monitored bands at power levels sufficient for interplanetary distances. The systematic nature of modern SETI searches makes undetected communication increasingly difficult for any hypothetical artificial objects. The strategic logic underlying disguised fleet scenarios faces fundamental questions about necessity and efficiency. Why would civilizations capable of interstellar travel choose elaborate deception when direct reconnaissance would achieve objectives more reliably? What advantage does camouflage provide when the target civilization lacks defensive capabilities against interstellar technology? The resource investment required for creating 7 sophisticated camouflage probes would exceed human economic output by orders of magnitude, suggesting that any civilization commanding such resources would have simpler approaches available. The darkest interpretation of our 7 comet convergence transforms celestial mechanics into existential threat, painting 2025 as a year of civilization-ending catastrophe. This doomsday narrative requires honest assessment of actual risks versus psychological fears that attach to unusual astronomical events. Real impact hazards follow well-understood physics, allowing precise calculation of collision probabilities and consequences. When asteroids or comets approach Earth on trajectories that might intersect our planet's orbital path, professional astronomers calculate encounter circumstances with mathematical certainty. The orbital mechanics governing these calculations operate with clockwork precision, leaving no room for ambiguity about genuine collision risks. None of our 7 comet cast members follows trajectories posing any impact threat to Earth during their current approaches. Pan-STARRS, SWAN, STEREO, Atlas K1, Atlas G3, LEMON, and NEAT all maintain safe distances measured in millions of kilometers. Their closest approaches place them far beyond gravitational influence zones that could lead to catastrophic encounters. 3. I-Atlas follows a hyperbolic trajectory, carrying it safely past all major solar system bodies. Its interstellar origin and high velocity relative to solar system objects actually reduce collision probabilities rather than enhancing them, since gravitational capture becomes impossible for objects moving at hyperbolic speeds. The absence of impact risk does not eliminate all potential hazards associated with enhanced comet activity. Space weather effects driven by solar maximum conditions can threaten technological infrastructure in ways modern civilization struggles to accommodate. Electrical power grids, satellite communication systems, and navigation networks all face vulnerabilities during periods of intense solar particle bombardment. But these technological risks stem from solar activity rather than comet behavior. Our star's 11-year magnetic cycle reaches maximum intensity in 2025, independent of any comet arrivals. The timing correlation between active comets and active solar conditions reflects shared response to solar system dynamics rather than causation flowing from comets to solar behavior. Quantifying risk requires statistical analysis, separating genuine threats from coincidental clustering that feels meaningful to pattern-seeking human brains. Professional risk analysis employs mathematical frameworks accounting for multiple comparison problems inherent in evaluating numerous potential correlations simultaneously. When testing many possible relationships between different event types, some apparent patterns emerge purely by chance, regardless of genuine causal mechanisms. The doomsday scenario gains psychological traction by bundling our 7 comet swarm plus 3, I-Atlas, into a single threatening entity, rather than treating each object as an independent phenomenon. This bundling transforms 7 separate low-risk events into one apparently high-risk situation, demanding immediate concern. Yet orbital mechanics does not recognize such artificial bundling. Each object follows its own trajectory, determined by gravitational forces operating independently for each comet. The apparent coordination exists in human perception, rather than physical reality, created by observation timing, rather than genuine interaction between objects. Historical precedent provides perspective on how unusual astronomical events relate to terrestrial disasters. Bright comets have appeared during periods of war, plague, famine, and social upheaval throughout recorded history. But careful analysis reveals no statistical correlation between comet appearances and increased rates of human catastrophe. The most elaborate conspiracy theory surrounding our 7 comet phenomenon suggests we are witnessing the initial phase of extraterrestrial invasion, disguised as natural astronomical events. In this scenario, 3i Atlas serves as a command vessel, coordinating a fleet of objects masquerading as traditional comets while conducting reconnaissance and preparing for eventual occupation of our solar system. This invasion hypothesis requires technological sophistication that staggers human imagination. Each alleged probe would need camouflage capabilities advanced enough to perfectly mimic spectroscopic signatures, outgassing behavior, and orbital characteristics of natural solar system comets. Such deception would demand intimate knowledge of our astronomical capabilities and detailed understanding of how genuine comets behave under solar heating. Consider the engineering challenges involved in creating artificial objects that could fool our most sophisticated instruments. Modern spectroscopy can identify molecular species with extraordinary precision, distinguishing between isotopic ratios that reveal formation environments and chemical processes. Any artificial probe would need to carry materials exactly matching composition, expected for objects formed in our outer solar system billions of years ago. The isotopic signatures pose particular challenges for hypothetical camouflage operations. Different stellar environments produce different ratios of hydrogen to deuterium, oxygen isotopes, and carbon isotopes. These ratios serve as cosmic fingerprints, identifying where materials formed and what processes shaped them. Solar system comets carry isotopic signatures consistent with formation in our primordial solar nebula. If any of our 7 visitors showed anomalous ratios suggesting formation elsewhere, spectroscopists would immediately flag the discrepancy. Outgassing behavior creates additional camouflage requirements. Natural comets develop their characteristic appearance through sublimation of volatile materials under solar heating, a process depending on internal structure, composition, and thermal properties developed over geological timescales. The brightness variations, jet formations, and tail development all follow predictable patterns based on how ice responds to increasing solar radiation. Artificial mimicry would require sophisticated engineering to replicate behaviors emerging naturally from comet physics. Light curves provide another avenue for detecting artificial origin. Natural comets typically show brightness changes reflecting tumbling motion of irregularly shaped objects under minimal gravitational binding. Communication requirements for fleet coordination present another vulnerability in camouflage scenarios. 7 distributed objects plus a command vessel would need frequent data exchange to maintain synchronized operations. Radio transmissions, laser communications, or other electromagnetic signals would carry information between fleet elements on timescales relevant to human detection capabilities. The SETI community operates radio telescopes, continuously monitoring for exactly these kinds of artificial signals. The strategic logic underlying disguised invasion scenarios faces fundamental questions about necessity and efficiency. Why would civilizations capable of interstellar travel choose elaborate deception when direct approach would achieve reconnaissance objectives more efficiently? What strategic advantage does camouflage provide when the target civilization lacks defensive capabilities against interstellar technology? The resource investment required for creating 7 sophisticated camouflage probes would exceed human economic output by orders of magnitude. Advanced civilizations capable of such investments would possess technological advantages so overwhelming that deception becomes strategically irrelevant. Furthermore, the invasion scenario assumes hostile intent without evidence of threatening behavior from any detected objects. None of our comet swarm members demonstrate capabilities beyond what natural objects should possess. 3. I-Atlas follows a departure trajectory, carrying it permanently out of the solar system, hardly consistent with establishing permanent presence for invasion purposes. Perihelion represents the moment of truth for any comet, the closest approach to our Sun when months or years of gradual inward spiral suddenly accelerate into a crescendo of activity. For 3 I-Atlas, this milestone carries particular significance because it marks the point where an interstellar visitor experiences the full intensity of our star's radiation and particle output. The physics of perihelion are both predictable and dramatic. As 3I Atlas draws closer to the Sun, solar radiation intensifies according to the inverse square law, doubling the brightness and heating power with each halving of distance. Ice that remained frozen during the long interstellar journey begins to vaporize, creating the gas and dust envelope that transforms a dark, inert chunk into a glowing, active comet. But the composition of interstellar ice likely differs from water-dominated mixtures characterizing solar system comets. 3 I-Atlas formed in the outer regions of another stellar system, where temperatures and chemical conditions might have favored different molecular species. Carbon monoxide, carbon dioxide, methane, and more exotic compounds could dominate its makeup. These compositional differences should reveal themselves through spectroscopic analysis during perihelion passage. Each molecular species produces characteristic emission lines when vaporized and excited by solar radiation. The spectrum of 3 I-Atlas will essentially serve as a chemical fingerprint of its birth environment, preserved across millions of years of interstellar travel. If our investigation uncovers genuine connections between 3 I-Atlas and the 7 comet swarm, perihelion provides the most likely window for dramatic revelations. The intense solar heating driving peak comet activity might also trigger whatever mechanisms could coordinate behavior among multiple objects. Observable signatures include sudden brightness increases, often marking vaporization of particularly volatile materials, or exposure of fresh ice surfaces as protective dust crusts erode away. These outbursts can boost a comet's brightness by factors of 10 or more within hours, creating spectacular observing opportunities while providing clues about internal composition and structure. Jets of material streaming from specific locations on 3 I-Atlas's nucleus could create asymmetric thrust effects, slightly altering the comet's trajectory. These non-gravitational forces are well-documented phenomena in traditional comets, but their presence in an interstellar visitor would provide unprecedented insights into how materials from other stellar systems respond to our Sun's influence. The development of 3 I-Atlas's tail system deserves particular attention because it offers real-time visualization of interaction between interstellar material and solar wind. Ion tails form when solar ultraviolet radiation ionizes comet gases, creating charged particles that stream away from the Sun under influence of the solar magnetic field. The behavior of this ion tail, its length, orientation, and response to solar wind variations will reveal how gases from another stellar system interact with our Sun's particle output. Any unusual characteristics compared to traditional comet tails might hint at compositional differences, distinguishing interstellar from local materials. Dust tails follow different physics, shaped by radiation pressure rather than magnetic forces. The size distribution and composition of dust particles determines how dramatically solar radiation can deflect them from ballistic trajectories. Large particles, barely deviate from original paths, while microscopic grains can be pushed into sweeping curved tails stretching across degrees of sky. The signatures we need to watch for during perihelion are both subtle and dramatic. Sudden brightness increases often mark the vaporization of particularly volatile materials, or the exposure of fresh ice surfaces as protective dust crusts erode away. These outbursts can boost a comet's brightness by factors of 10 or more within hours, creating spectacular observing opportunities while providing clues about internal composition and structure. Professional observatories and amateur astronomers worldwide coordinate observation campaigns to ensure continuous monitoring during these critical periods. Jets of material streaming from specific locations on comet nuclei create asymmetric thrust effects that slightly alter trajectories. These non-gravitational forces are well-documented phenomena in traditional comets, measured through precise astrometric tracking over weeks and months. The jets act like natural rocket engines, pushing the comet in directions determined by which areas of the surface are actively vaporizing and how the nucleus rotates. For 3I Atlas, jet activity would reveal how interstellar materials respond to solar heating compared to native solar system ices. The development of tail systems provides real-time visualization of comet activity, visible even to casual observers. Ion tails form when solar ultraviolet radiation strips electrons from comet gases, creating charged particles that stream away under influence of the solar magnetic field. These tails always point directly away from the sun, regardless of the comet's direction of motion, sometimes extending for tens of millions of kilometers in spectacular blue spikes visible in photographs. The length and brightness of ion tails depend on how much gas the comet produces and how active the solar wind happens to be during the observation period. Dust tails follow different physics, shaped by radiation pressure rather than magnetic forces. Sunlight physically pushes dust particles away from the comet, but the effect depends strongly on particle size. Microscopic grains experience strong radiation pressure and sweep into curved tails that can span huge angular distances across the sky. Larger particles barely respond to radiation pressure and follow ballistic trajectories close to the comet's orbital path. The ratio between dust and gas production reveals information about surface composition and internal structure. Fragmentation events represent the most dramatic possible outcome of perihelion passage. The combination of solar heating, rotational stress, and internal pressure from vaporizing volatiles occasionally proves too much for a comet's weak gravitational binding. The object breaks apart, sometimes splitting into multiple fragments that separate along the orbital path. Historical examples include Comet Shoemaker Levy 9, which fragmented during a close pass by Jupiter before the pieces crashed into the giant planet in 1994. For 3I Atlas, fragmentation would be particularly significant because it would provide access to interior materials that have remained unaltered since the comet's formation in another stellar system. The fresh surfaces exposed by breakup would offer unprecedented opportunities for spectroscopic analysis of truly pristine interstellar materials. However, fragmentation would also complicate our investigation of potential connections to the 7 comet swarm by creating multiple objects where previously one existed. Amateur astronomers worldwide are preparing observation campaigns to monitor 3I Atlas through its perihelion passage, providing distributed coverage that no single observatory could match. This citizen science network will generate continuous light curves, photographic documentation of tail development, and real-time alerts if dramatic outbursts or fragmentation events occur. The democratization of astronomical imaging means hundreds of observers contribute data supplementing professional monitoring programs, multiplying observational capabilities beyond what any single institution could achieve. Modern amateur equipment rivals professional capabilities from just decades ago. Digital cameras with cooling systems reduce electronic noise to levels allowing detection of extremely faint objects. Computerized telescope mounts track celestial targets with precision measured in arc seconds, compensating for Earth's rotation automatically. Image processing software stacks multiple exposures to enhance signal while suppressing noise, pulling details from data that would appear blank to visual observers. An amateur astronomer with modest investment can now collect data quality that required major observatory access in the 1980s. The distributed nature of amateur networks provides advantages beyond raw collecting power. Professional observatories face scheduling constraints, weather limitations, and competing demands for telescope time. A single cloudy night can create gaps in monitoring campaigns that miss critical events. Amateur networks spanning multiple continents ensure that someone somewhere probably has clear skies when interesting phenomena occur. If 3i Atlas produces a sudden outburst visible only for a few hours, distributed observers increase the probability that someone captures the event. Social media and online forums facilitate rapid information sharing among amateur communities. When one observer detects unusual activity, alerts spread within minutes to observers at other locations who can confirm and extend the observations. This real-time coordination transforms isolated individuals into functioning research networks, operating with efficiency approaching professional collaborations. The data flows into public databases where professional astronomers access it for formal analysis, creating genuine partnerships between amateur and professional communities. Photography forums dedicated to comet imaging buzz with activity during 2025, as observers share images of multiple targets developing simultaneously. The technical discussions cover optimal exposure times, filter selections for enhancing specific spectral features, and processing techniques for bringing out faint tail structures. Experienced imagers mentor newcomers, sharing decades of accumulated knowledge about comet photography techniques. The educational value extends far beyond the specific objects being observed, building skills and understanding that participants carry into future astronomical pursuits. Time-lapse sequences created by amateur observers provide unique perspectives on comet evolution. By imaging the same comet every clear night for weeks or months, observers document changes in tail structure, brightness variations, and responses to solar activity. These sequences reveal dynamics invisible in single snapshot observations, showing how comets breathe and respond to their changing environment as they approach the Sun. Professional researchers use these amateur time series to supplement their own observations, filling temporal gaps and extending baseline coverage. The parallel monitoring of all 7 traditional comets during the same period creates unprecedented opportunities for comparative studies. Observers can document how different comets respond to identical solar conditions, revealing compositional and structural differences through their behavioral variations. Fragmentation represents the most catastrophic failure a comet can experience. The moment when structural integrity collapses under stresses that weak gravitational binding cannot resist. The combination of solar heating, rotational forces, and internal pressure from vaporizing volatiles creates mechanical loads that occasionally exceed what fragile ice and dust structures can withstand. When failure occurs, the comet breaks apart in events that unfold over hours or days, splitting into multiple fragments that separate along the orbital path. Historical examples provide templates for understanding fragmentation processes. Comet Shoemaker Levy 9 broke apart during a close pass by Jupiter in 1992, torn into more than 20 distinct fragments by tidal forces during its approach to the giant planet. The pieces continued orbiting Jupiter independently until they crashed into the planet's atmosphere 2 years later, in a series of spectacular impacts visible from Earth. Comet Linear fragmented in 2000 as it approached the Sun, disintegrating into a cloud of debris that never recovered its original brightness. The mechanisms driving fragmentation vary depending on comet structure and environmental stresses. Thermal stress occurs when solar heating creates temperature gradients between sunlit and shadowed regions, causing differential expansion that can crack brittle materials. Rotational stress increases as outgassing creates asymmetric thrust that spins the nucleus faster, eventually exceeding the weak cohesive forces holding rubble pile structures together. Internal pressure builds when subsurface ice vaporizes faster than gas can escape through surface layers, creating stress that can explosively excavate fresh material. For 3I Atlas, fragmentation would provide unprecedented scientific opportunities alongside observational challenges. The exposure of interior materials untouched since formation in another stellar system would allow spectroscopic analysis of pristine interstellar composition. Fresh ice surfaces would show different activity patterns than weathered exterior layers, revealing how cosmic radiation and interstellar environment modified surface chemistry during the long journey. The size distribution and separation velocities of fragments would constrain models of comet internal structure and mechanical properties. However, fragmentation would complicate investigation of potential connections to the 7-comet swarm by replacing one target with multiple objects requiring independent tracking. Each fragment would follow slightly different trajectory, determined by the velocity it acquired during breakup. Separating genuine coordinated behavior from the geometric complexity of tracking related fragments would become significantly more difficult. If unusual timing correlations appeared between fragment events and activity in other comets, distinguishing meaningful patterns from coincidental clustering would require even more careful statistical analysis. Observers worldwide maintain fragmentation watch protocols during perihelion passages, monitoring for telltale signatures that precede catastrophic breakup. Sudden brightness increases can indicate major structural changes as fresh ice becomes exposed. Elongation of the nuclear condensation, the bright central region in comet images, sometimes precedes visible splitting as internal fractures propagate. Changes in tail morphology can reflect altered outgassing patterns from a nucleus under increasing stress. After months of investigation, tracking orbital mechanics, analyzing statistical probabilities, and examining every conceivable connection between 3I Atlas and our 7-comet parade, the evidence points toward a conclusion that is simultaneously reassuring and remarkable. We are witnessing an extraordinary natural phenomenon rather than evidence of exotic coordination or extraterrestrial intervention. The 7-comet swarm of 2025 represents genuine statistical clustering that captures attention precisely because such concentrations occur rarely enough to feel meaningful. Pan-stars, Swan, Stereo, Atlas K1, Atlas G3, Lemon, and Neat are following independent orbital paths determined by gravitational forces that began shaping their trajectories millions of years ago, long before human civilization existed to witness their eventual convergence. The investigation has revealed no orbital relationships, behavioral anomalies, or timing correlations that exceed what statistical analysis predicts for independent objects influenced only by conventional gravitational and solar heating effects. Each comet tells its own story of formation in the outer solar system, gravitational perturbations that initiated its current orbit and response to increasing solar radiation as it approaches perihelion. Pan-stars originated from the Oort cloud, perturbed onto its current path perhaps 1 million years ago. Swan carries compositional signatures consistent with formation in cold outer regions before being scattered outward. Stereo developed its sun-grazing trajectory through gradual modifications over thousands of years. The Atlas twins, despite sharing discovery circumstances, approach from different angles with different orbital histories. Lemon shows clear evidence of a Neptune encounter 50,000 years ago that determined its 2025 arrival. Neat has been tracked for 15 years with orbital elements refined to extraordinary precision. When we compare all 7 orbits systematically, searching for common signatures indicating shared influences, we find nothing beyond the temporal clustering that initially caught our attention. Each approaches from different directions with different inclinations, different eccentricities, and different source regions spanning the entire outer solar system. If some massive object had been gravitationally shepherding these arrivals, consistent perturbations would appear in their orbital elements, pointing toward a common cause. No such signatures exist. Electromagnetic coordination scenarios fail even more decisively. The forces required to alter comet trajectories through magnetic field interactions would exceed anything observable in the solar system by orders of magnitude. If powerful electromagnetic fields were manipulating our visitors, every observatory would detect unmistakable spectroscopic and behavioral signatures. The data shows only normal responses to solar wind and radiation pressure consistent with natural comet behavior. 3. I-Atlas adds wonder as our solar system's first well-documented interstellar visitor, exhibiting clear comet-like behavior. This object carries ice and dust forged around another star, now vaporizing under our sun's heat to create tails making alien chemistry, visible to telescopes worldwide. The timing correlation between our interstellar visitor and the most active comet year in recent memory continues to intrigue researchers. But current evidence suggests coincidence rather than causation. The statistical clustering that characterizes 2025 provides insights into long-term solar system dynamics operating on timescales exceeding human historical records. Comet arrivals follow roughly random distributions across time, with occasional concentrations that rarely exceed 2 or 3 objects. 7 comets arriving within months represents a statistical outlier, but outliers occur naturally in any sufficiently large dataset. The question is whether this clustering exceeds bounds of reasonable coincidence, or falls within expected variation for random processes. Probability calculations depend on defining the observation window and counting rules carefully. If we ask about the chance of exactly 7 comets arriving in a single specific year chosen in advance, the probability appears vanishingly small. But if we ask about the chance of some year eventually showing unusual clustering, when we examine centuries of data, the probability increases dramatically. Rare events become likely when given enough opportunities to occur. The improved detection capabilities of modern surveys affect these calculations in subtle ways. We find more comets overall because automated telescopes scan more sky more frequently than human observers ever could. But the percentage becoming bright enough for public attention remains relatively constant with historical patterns. Survey improvements announce arrivals sooner without creating brightness where none would naturally occur. The 7 comets of 2025 were always going to brighten, regardless of our detection capabilities. Solar maximum timing adds visual drama through enhanced tail behavior and increased activity levels. The 2025 peak in the 11-year solar cycle creates space weather conditions, amplifying every aspect of comet appearance. Ion tails grow longer and brighter under stronger solar wind. Disconnection events occur more frequently during magnetic storms. The same objects would appear dimmer and less active during solar minimum, but their fundamental clustering would remain unchanged. The convergence creates unprecedented opportunities for comparative comet studies rarely achieved within single observing seasons. Researchers can study how different compositions, sizes, and orbital geometries respond to similar solar heating conditions, advancing understanding of comet physics in ways isolated observations cannot achieve. Multiple bright comets provide amateur astronomers with photographic targets, generating skills and enthusiasm that persist long after 2025 passes into history. The public engagement generated by our investigation demonstrates how unusual astronomical events catalyze interest in space science and critical thinking skills. The process of evaluating extraordinary claims against available evidence provides educational opportunities traditional astronomy outreach rarely achieves. Learning to distinguish between correlation and causation, to evaluate claims against appropriate standards, and to maintain wonder while demanding rigor provides intellectual tools serving society well beyond specific comet contexts. The absence of exotic connections does not eliminate all possibilities for future discoveries. Continued monitoring might reveal subtle correlations current analysis has missed, or closer approaches might enable detection of characteristics remaining below present observational thresholds. Science progresses through incremental improvements in measurement precision and analytical techniques, occasionally revealing previously hidden phenomena. The message of the 2025 swarm may ultimately be that the universe provides enough genuine wonder without requiring us to invent additional mysteries. 7 independent comets converging through natural processes, while an interstellar visitor makes its first and only passage through our solar system, represents a cosmic coincidence worth celebrating for its own remarkable timing. The education value of this experience extends far beyond astronomy to critical thinking skills, applying across all domains of human knowledge. Learning to distinguish between correlation and causation, to evaluate claims against appropriate evidence standards, and to maintain wonder while demanding rigor provides intellectual tools serving society in contexts having nothing to do with comets. The process we followed examining extraordinary hypotheses while maintaining skepticism proportional to the claims being evaluated demonstrates how scientific inquiry addresses exotic possibilities without becoming captured by speculation. The tools of modern astronomy provide unprecedented capabilities for distinguishing between genuine anomalies and apparent patterns emerging from normal statistical variation. These same tools reveal universe-scale phenomena exceeding human imagination without requiring exotic explanations, demonstrating that reality often surpasses the creativity of speculation. The Seven Comet Swarm alongside 3I Atlas creates a celestial festival, providing opportunities for comparative studies, public engagement, and deeper understanding of outer solar system dynamics. Professional astronomy will continue systematic observation and analysis of all unusual objects, maintaining vigilance for characteristics that might indicate artificial origin or exotic physical processes. The community takes such possibilities seriously while applying appropriate evidentiary standards, distinguishing between legitimate anomalies and statistical fluctuations in complex datasets. Future observers may look back on 2025 as a watershed year when improved survey capabilities and social media attention combined to transform routine astronomical discoveries into cultural phenomena engaging millions worldwide. The broader implications extend beyond specific questions about connections between interstellar visitors and traditional comets. The investigation demonstrates how rigorous scientific inquiry can address exotic hypotheses without becoming captured by speculation those hypotheses generate in popular culture. Maintaining balance between curiosity and skepticism becomes increasingly important as social media algorithms amplify sensational claims faster than careful analysis can evaluate them. The 2025 Comet experience illustrates how pattern-seeking human psychology transforms objective astronomical events into subjective narratives about cosmic significance. This transformation is not necessarily problematic. Finding meaning and wonder in celestial phenomena has inspired human cultures throughout history, but it requires conscious separation between factual observations and interpretive frameworks that give those observations emotional resonance. The swarm's ultimate message may be that human curiosity and analytical capability, rather than exotic cosmic coordination, represent the most remarkable aspects of this entire experience. We have developed tools sophisticated enough to detect interstellar visitors, calculate orbital elements with extraordinary precision, and evaluate extraordinary claims through rigorous statistical analysis. This technological and intellectual achievement deserves recognition alongside any spectacular celestial phenomena we are privileged to witness. The universe may not be sending us messages through coordinated comet arrivals, but it continues providing opportunities for discovery that reward careful observation with deeper understanding of our cosmic environment. The investigation concludes where it began, with wonder at unusual timing, respect for rigorous analysis, and appreciation for a universe supplying enough authentic mystery to occupy human curiosity for millennia to come. Hypothesis tested, evidence evaluated, wonder preserved intact for future investigations awaiting beyond our current observational horizons.